Hey everyone, welcome back to the Maths for Machine Learning series. In this video, we're diving into one of the most fundamental concepts, probability basics. Before we get into the heavy formulas later on, let's first build a solid foundation. We'll talk about what random experiments are, what outcomes mean, what a sample space is, and finally, what we call an event. And we have some more topics after that too. So let's start. First, we start with a random experiment. So, a random experiment is simply any process or action that can produce one or more possible results, but we can't predict exactly which result will occur. Let me give you a few examples. So, when you toss a coin, you might get either a head or a tail, but you can't know which one for sure before you toss it. Similarly, when you roll a die, you might get any number from 1 to 6. Again, you know the possibilities but not the actual outcome. And finally, when you draw a card from a deck, you could get any one of the 52 cards. So, in short, a random experiment always carries uncertainty. You know what could happen, but not what will happen. Next, we move on to the outcome. An outcome is the result of doing one trial of that random experiment. For instance, if you toss a coin once and it lands on head, that's one outcome. If you roll a die and get a 4, that's another outcome. And if you draw a card and if it turns out to be the king of hearts, that's also an outcome. And remember, if you repeat the experiment, say toss the coin multiple times, you may get various outcomes each time. So each individual result is called an outcome. Next, we move on to the sample space. The sample space is simply the set of all possible outcomes for a given random experiment. For example, when you toss a coin, the sample space contains two elements, head and tail. When you roll a die, the sample space has 6 elements, 1, 2, 3, 4, 5 and 6. So, you can think of sample space as the complete list of everything that could possibly happen. Now comes the idea of an event. So, any event is an specific sorry an an event is any specific part of subset of that sample space. In other words, one or more outcomes that we care about. So here are a few examples. If we say getting a head when tossing a coin, that's an event. It includes just one outcome, head. Similarly, if we say getting an even number when rolling a die, that event includes a number 2, 4 and 6. And finally, if we say drawing a red card, that event includes all the hearts and diamonds in the deck. So basically, the sample space is the world of all the possibilities. And an event is a smaller part of that world that we're focusing on. Now, why do all of these matters in case of ML? Well, they do matter a lot. In ML, data often comes from random processes. For example, whether a customer buys a product, how a stock price moves, or whether an email is spam or not, each of these observations can be seen as an outcome from a random experiment. Understanding how to explain and measure these outcomes using probability helps us make predictions and in uncertain situations. For instance, we might want to find the probability that a customer will buy something after clicking an ad, or the chance that probably a mail is spam given the word it contains. This way of thinking in terms of random experiment, outcome and events is the very foundation of probabilistic model like naive Bayes, Bayesian ML and many optimization approaches that rely on randomness such as stochastic gradient descent. Next, we go to our probability range rule. We'll start with a very simple but powerful idea here. So, the probability range rule, as shown here, says that the probability of any event, we'll call it P of A, will always lie between 0 and 1. So, this is the mathematical form of it. Now, what does this mean? If P of A equals to 0, then we can say that the event is impossible. It can never happen. For example, rolling a 7 on a normal 6-sided die, that's impossible, so its probability is 0. Similarly, if P of A equals to 1, the event is certain. It will definitely happen. For example, getting a number less than 7 when rolling a die. That's guaranteed. So the probability is 1. And if the value is between 0 and 1, and if both are not inclusive, then the event is possible but uncertain. For example, getting a 4 when rolling a die, it is possible but not guaranteed. The probability there is 1/6. You can think of probability like a confidence scale. 0 means no chance at all, and 1 means complete certainty. Everything else falls somewhere in between. Next, we move on to addition rule of probability. It is written in this particular form as shown in the formula here. We'll break it down shortly. When we say A union B, written as the following, it means A or B, which covers all cases. Either A happens or B happens or both happen together. Similarly, A intersection B, which is denoted by this particular symbol, means A and B, which means the event where both A and B happen at the same time. We'll understand this with an example. Suppose we have a 52 deck playing cards or a deck of 52 playing cards. We'll define a few events. Event A is drawing a king. There are 4 kings in the deck, right? So the probability of event A happening is 4 by 52. Similarly, event B is drawing a heart. So there are 13 hearts in total. So the probability of event B is 13 out of 52. Similarly, we consider drawing king of hearts. That means the event A is drawing a king, and then event B is drawing a heart. So if we combine this, we can say that the probability of A intersection B is equal to 1 by 52, because in our deck of cards there is only one king of hearts. Now if we plug this into a formula, we can easily compute the probability of drawing a king or drawing a king of heart. But you might be wondering, why are we subtracting PA intersection B here? If we simply added PA and PB, the king of hearts would be counted twice, once in the king's group and once in the hearts group. So to fix that double counting, we subtract the overlap, that's PA intersection B. This ensures that the final probability is accurate. We'll look at 2 special scenarios in this particular case here. The first one is mutually exclusive events. These are events that can happen together. That means PA intersection B equals to 0. In that case, the formula becomes much more simpler here, reducing the term PA intersection B from the equation 1 that we saw earlier. Example, if rolling a 2 or a 5 on a die, you can't get both at the same time. They're mutually exclusive. Similarly, the other is independent events. These are events that do not affect each other. Here, the intersection is given by the multiplication. So, PA intersection B equals to PA multiplied by PB. Example, flipping a coin and rolling a die. Each outcome does not affect the other in this particular case. So, to summarize, the probability range tells us that every probability lies between 0 and 1, and the addition rule helps us find the probability of either of 2 events happening without double counting any overlap. Now we'll dive into dependent and independent features. This is one of the most fundamental ideas that helps us understand how randomness behaves in real world situations and in ML models. We'll start with independent event. So 2 events are said to be independent if the outcome of one does not affect the outcome of the other. Think of this simple example. So you flip a coin and roll a die. So event A is getting a head on the coin and event B is rolling a 4 on the die. Now what happens with the coin has no effect on the number shows up on the die. They're completely independent. Mathematically, for independent events, the probability of both happening together is the product of the probability of each event happening. Next, we move on to dependent events. Two events are dependent if the outcome of one does affect the probability of the other. We'll take an example. Drawing cards from a deck without a replacement. Event A, suppose we say, is drawing a king on the first draw. So basically the probability is 4 out of 52. And then event B is drawing a king on the second draw. But now one king is already gone and only 51 cards remain. So the probability becomes 3 out of 51. See, the probability of the second event changed because of what happened first. That means these two events are dependent. Mathematically, they are represented using this particular formula here. Here, P given A simply means the probability of B occurring after A has already happened. So, this is all for this video. If you enjoyed learning from this video and are finding our Math for ML series helpful, please give this video a like, share it with your friends and subscribe to the channel. Most of our viewers watch our videos regularly but haven't subscribed yet. So, if you're one of them, please hit that subscribe button. It's free for you, but it means the world to us and keeps this series going strong. So with that request, I'll see you in the next video.